So how do we do counterbalancing? There are some easy cases which includes the situation when the order effects is evenly distributed between the treatment conditions, and it doesn't matter which treatment comes first. So if we have a situation in which no matter which treatment comes first, there are like 5 points change due to the order effect, that's the easy case. For example, if you look at this chart, if you do a repeated measure using pop music and classic music as a background music for studying, and you believe that listening to pop music has no effect on classic music, then most likely there is no order effect. However, if you give your participant a generic kind of medicine and then later you give them a brand name type of the same medicine, and there is a reason that like there is a 5 points carryover or order effect for all participants, then we can use counterbalance to avoid the carryover effect. And the way it works is that for half of the participants we use the generic medicine first and the brand medicine later, and for the other half we use the brand medicine first and the generic medicine later. This way we counterbalance the 5 points carryover effect between the two groups. However, we need to know the limitations of counterbalancing. First, counterbalancing, although balances the effect of ordering effect, but it doesn't eliminate it. So we just make it equal for both groups, but it doesn't mean that we eliminate the actual order effect, and so both means are inflated. The other limitation is when counterbalancing adds order effect to some of the individuals but not to all. So most of the time it's not as easy as the example I just gave you, that the order effect is not 5 points for every single person. So for some people we have 5 points, for some people we have 6 points, and we never know how much order effect we have. And the other limitation is when the order effect is not symmetrical, which means it matters which treatment goes first, because sometimes one treatment has a carryover effect, but the other one doesn't. For example, if I teach you statistics first and then I teach you math, probably there is not much carryover effect. But if I teach you math first and then statistics, probably that could help you with your statistics. So in such situations, the counterbalancing does not balance the order effects. Another limitation is when you have only two treatments, probably it's easy and it's possible to do the counterbalancing. But imagine that we have like 4 or 5 different treatments, and if we want to do counterbalancing, then we have to have look for 4 or 5 subgroups and also different combinations of the order in which we put the treatments together. For example, if we have like 4 treatments, 4 conditions, there are going to be 24 ways in which we can put the treatments in order, and this is going to make it very complicated and close to impossible to make such an arrangement. Therefore, sometimes instead of doing a whole counterbalancing, we do a partial counterbalancing, which means instead of like doing 24 different conditions or 24 different order, we use a simple method called Latin square, in which we only use a limited number of orders. For example, instead of doing 24 different conditions, we use only 4 different conditions. And if you look at this chart, it shows that each treatment comes first only once. But still, as you see, it's possible that we have treatment B right after A in this case and in this case and in this case, and we, for example, never have treatment D right after A, and we never have treatment D right after treatment A. So it's not a perfect, but it's a doable and practical solution when we're having more than two treatment conditions. Or instead of doing the Latin square, we can just randomly change the orders, like only 4 or 5 conditions and total random order. We put them together to do the counterbalancing, and to be able to compare the different treatments. The statistical analysis that we use to do a within subject design or repeated measure depends on how many treatments we have. If we have only 2 treatments, we use a t-test for repeated measures or paired samples, and if we have more than 2 treatments, then we use a single factor ANOVA for repeated measures. And finally, if there is a specific situation in which we don't have scores or grades for our participants and we only have their ranks, we use the Wilcoxon test. And if the situation is even worse and we don't even have the ranks and we only have the nominal scale like pass and fail or yes and no, then we use the sign test instead of ANOVA or t-test. And at the end, there is a situation that we sort of combine the between subject and within subject, because like I said, there are some limitations with between subject and there are some limitations for within subjects. So instead of having a totally different groups in between subjects, we match the 2 groups in terms of a few variables that we are worried, and then if we do that, then we have 2 equivalent groups to compare. So the groups are comparable and we don't have the carryover or the order effect. So that's a solution that we can use in situations where it's possible to match subjects based on specific variable.